Okay, we're going to talk about weight and balance. Weight and balance is going to break down, per the PTS, into 4 distinct sections. We're going to discuss the terms, their meaning, maybe give some visual cues for those terms. We're going to talk about weight and flight performance, weight and balance control, some things that we can do, how we determine the weight and balance, and also per the PTS, any kind of changes that occur when adding, removing, or shifting weight. Okay, now we're going to talk about some terms common to weight and balance. The first one would be a reference datum, and the manufacturer specifies a horizontal line that goes through the aircraft, which we take measurements from, and that can be out in front of the aircraft, it can be on the firewall of the aircraft, and it could be even a little bit further back towards even the leading edge of the wing. So that's our reference datum. And the next thing would be an arm. And an arm is a measurement from a reference datum. So if we had one, say, right here in our aircraft, and we wanted an arm to, say, maybe a cargo area back here, the measurement from that reference datum to that cargo area would be an arm. And a station would be an area such as this. And so let's say this arm was 145 inches. We would call this cargo area maybe something like station 145 in our POH. So that would be a station. Now, one thing to keep in mind is a weight, an arm times the amount of weight at that arm creates a moment. And a moment is the tendency for an object to rotate about an axis. So, for example, if we took our aircraft right here, I can use the distance between my center of gravity and my rudder. That's also an arm. And any type of force applied at that distance, so if I step on my rudder pedal, that distance between the center of gravity and that weight is going to create a moment. And that moment might be with that situation would be a yawing tendency to this side. So that's a moment. The center of gravity in the aircraft, which is usually depicted like this right here, okay, the center of gravity for an aircraft is where the axes of the aircraft run through. So if the aircraft was suspended on a string, this is where the aircraft would balance at. So if you look at our longitudinal, our lateral, and our vertical axes, run through the aircraft, that would be the center of gravity. Now, the center of gravity is determined by taking the total moments of the aircraft divided by the total weight. And that will tell us where the center of gravity is located in the aircraft. Now, the center of gravity limits, those would be the extreme forward and aft limits of where our center of gravity can be located for a given weight for flying. So next thing we'll talk about is a few of the different definitions for the weights in the aircraft. The first is the usable fuel. And the usable fuel is the amount of fuel inside the aircraft that we can use for flight. Unusable fuel in the aircraft, some of the fuel we're not able to use because it stays in the system, and that unusable fuel is not available for flight planning because it's just not. Basic empty weight is the standard weight of the aircraft, the optional equipment that's installed in the aircraft. Our usable fuel, full operating fluids, includes things like oil and our hydraulic fluid. The payload of the aircraft is the flight crew, the passengers, the baggage, or any kind of cargo. The useful load is the difference between the takeoff weight and the basic empty weight of the aircraft, which we just discussed. The max ramp weight. Max ramp weight is a little bit higher than our maximum takeoff weight. that we can be at. It accounts for some extra fuel being in the aircraft for startup, run up, and taxi to the active runway. Our maximum takeoff weight is the maximum weight that we can be at when we start our takeoff roll. Maximum landing weight is the maximum weight that we can be at when we attempt to land the aircraft. Keep in mind that some types of aircraft, the maximum takeoff and landing weight, an aircraft might be over the maximum landing weight when they take off. In those cases, aircraft usually, if they have to turn around and make an emergency landing, they have to dump some fuel. Just one of those little things that I wanted to kind of bring up. Max zero fuel weight. So that's the max weight when we take out the usable fuel in the aircraft. And a few standard weights as rules of thumb that are good to know. In terms of gallons, a gallon of aviation gas weighs 6 pounds. A gallon of jet fuel weighs 7 pounds. A gallon of oil weighs 7.5 pounds. And a gallon of water weighs approximately 8.3 pounds.
We're going to talk about weight and balance characteristics and how that affects an aircraft's performance. Obviously, the best scenario is to have your weight and balance within the CG limits. We're going to talk about what happens if you have your CG forward and aft, either in or out of those limits, especially if you have an overloaded airplane as well, not necessarily out of CG, but just overloaded, and some of the factors that can affect your performance based on that. Go ahead and start with our overloaded aircraft characteristics. It's going to have a higher takeoff speed and require a longer ground roll to get going because you're going to require a higher angle of attack, and we will demonstrate how that works in just a moment. You're going to have a reduced rate and angle of climb, a lower maximum altitude, also a shorter range. Your cruising speed will be reduced, and we'll explain how that works. Reduced maneuverability, also a higher stalling speed and higher approach speed. Your landing speed will also be higher, and that will therefore increase your ground roll distance. And you may have excessive weight on the landing gear of the aircraft. So let's go ahead and talk about, we've got our lift equation here. We'll get to that in just a moment. But what it is, lift times density, altitude times your coefficient of lift times the surface area times velocity squared divided by 2. And what we have is two aircraft, exact same type of aircraft, was called a Cessna 172, and this one's loaded heavier than this one. Our arrows are indicative of our weight. The heavier aircraft is going to require more lift, obviously, to become airborne than our lighter aircraft will. So it's quite simple. How do we create more lift for this heavier aircraft? Well, we can't change the density altitude because we're saying that both of these aircraft are taking off, on parallel runways right next to each other. We're given a similar scenario. The surface area is not going to change because we're going to take off both aircraft either with or without flaps. It's going to be this condition is going to be simulated both the same for both aircraft. And our velocity, we're going to assume that they're both taking off at the same speed, or attempting to take off at the same speed. So what's going to happen is we need to increase our coefficient of lift since all of our others are a constant. So what do we do to increase our coefficient of lift? So we've got to have a higher angle of attack. And also that will lead us to have a higher takeoff speed. But just for this scenario, we're going to focus on the coefficient of lift increase. With this aircraft here, let's say that it's got an angle of attack of 5 degrees. This aircraft must produce much more lift to overcome the excess weight. So it may have an angle of attack of 10 degrees. And to be able to produce an equivalent amount of lift for the weight it has, and this one will have to produce an equivalent amount of lift for the weight that it has, and thus has to produce less lift. Let's go ahead and talk about the location of the CG in the aircraft and how that affects the characteristics of the aircraft. This has a lot to do with the moments and arms that Andy mentioned earlier. we have an aircraft, CG where it's supposed to be, and we're loading a bunch of baggage and passengers, everything into it. And we're not doing our proper weight and balance. We find that our CG is located too far back. Not necessarily too far back, but it's further back than the CG here. Our elevator effectiveness and rudder effectiveness is decreased. Why is this? Well, we see the distance between our CG, which we know is the point at which the aircraft pivots about. And the longer the arm, the easier it is to control an aircraft. It's quite simply like if you're trying to loosen a stuck bolt. You're not going to use a very small wrench. You want a wrench with a long arm, and that gives you, the law of lever, it gives you more force to apply. So if we're, for this instance, we're trying to add some rudder force to this aircraft, which one is going to have the greatest control surface effectiveness? Obviously the one with the longest arm, because it's going to have more force. So let's say if we have an arm of 100, and this force, let's just say is equivalent to 10. These are just numbers that we make up for this scenario. This has a total moment of 1,000, and we can call that inch pounds, foot pounds, whatever we want. This is just a scenario. So this one here, let's say this is only 80. And same thing, we give a rudder force of 10. This is only going to have a moment of 800. So that goes to show how your control surface effectiveness is decreased. And the same holds true for the elevators as well. So I'll also talk about our stalling characteristics based on location of CG. If an aircraft is either too heavy or has a CG located too far aft, let's use that for this scenario. Our CG is too far aft means we don't have as much nose down, and so the plane doesn't need as much tail down force to compensate for the nose down force that airplane has on its own. And so therefore we're going to be able to fly at a lower angle of attack because we don't have to have that tail down force. I'm sorry, the horizontal stabilizer will be at a lower angle of attack because we don't need to have that tail down force. And therefore we're creating less induced drag by that lifting force not being applied. And so we're going to be able to cruise a little further, we're going to cruise a little faster, and we are going to stall at a lower airspeed simply because we're already flying, the airplane itself is flying at a lower angle of attack. But when we do stall, we're going to have bad stall recovery characteristics simply because, as we mentioned before, this is a shorter arm and our control surface effectiveness is decreased. Now, if we have a CG that's further forward, we're going to have greater control surface effectiveness because we have a longer arm. And in stall recovery, the first thing we want to do is get the nose down. This has got a CG that's further forward. It already has that nose down tendency. But with the nose down tendency, as we learned earlier, we have to have a tail down force to counteract that. So we're going to have a higher angle of attack on our horizontal stabilizer at all times to keep that plane in straight and level flight. What that's going to do is going to cause the entire aircraft to pitch up. So this aircraft is going to be flying at a higher angle of attack just because we have this increased tail down force. Not the best airplane in the world. Because we have to have this increased tail down force to counteract that forward CG. That tail down force is helping push our nose back where it's supposed to be to get us a straight and level flight. Because of this, our relative wind is right here. There's our angle of attack. We're flying at a high angle attack already, just in straight and level cruise flight. Therefore, we don't have much more angle to work with before we stall, because a stall is always on set at a certain angle of attack, which is known as the critical angle of attack. So if we're flying already with a higher angle of attack, then we will stall at a higher speed because of that. Also, a forward CG, because we're talking about that, will not help you land. Well, how's that? If you got a forward CG, it's a little more difficult to flare the aircraft. You have greater control effectiveness, as we mentioned, because of the longer arm, but as we mentioned earlier, at lower airspeeds, the control effectiveness of the elevator is diminished. So therefore, you may have difficulty in flaring the aircraft. You could have a three-wheel landing or even a nose landing and may cause damage to the landing gear, nose wheel, or the prop in an aircraft that's a little further aft on the CG. The flaring won't be too difficult. May actually have to require a little bit of forward pressure to keep it from tipping back too much. But your landing characteristics for the aft CG are more desirable in that case. So we talked about CG and how that affects the flight characteristics, the stall recovery characteristics, and the takeoff and landing characteristics of an aircraft. Let's talk about the structural integrity of an aircraft. An aircraft in the normal category is rated to be able to withstand 3.8 positive Gs and 1.52 negative Gs. In the utility category, that goes up to 4.4 positive Gs and 1.76 negative Gs. And then the aerobatic category is a positive 6 G load and a G load of negative 3. So let's say, for instance, we're flying an aircraft with 2,000 pound max gross weight. And at 3.8 Gs, which we already know from the normal category is the maximum it can withstand without structural damage, it can withstand a load of 7,600 pounds. So that's if you take 2,000 times 3.8, it's a load of 7,600 pounds. But if you overweight that aircraft by just 200 pounds, so if you have the aircraft flying at 2,200 pounds, to achieve that 7,600 max load, you only have to pull 3.45 Gs. So the limit that the aircraft says is okay to fly within can be exceeded before you actually reach that G number, just because you have overloaded your aircraft. So that's definitely something we need to take into consideration. Always do proper weight and balance, and if you do have any questions, always seek the AFM, POH, and make sure that you're flying safely.
Okay, we're going to talk about methods of airplane weight and balance in terms of control, and a couple key points to understand when we're talking about that is what we can control and what we can't control. Well, there's nowhere specifically in the Federal Aviation Regulation that says that we're required to do a weight and balance. However, Federal Aviation Regulation 91.9 says that we must comply with any limitations set forth in the Pilot Operator Handbook. So, Pilot Operating Handbook, Airplane Flying Manual for the aircraft is going to have a weight and balance listed inside of it. And we definitely want to make sure that we comply with the CG ranges. So it really is crucial, even though we're not required to do a weight and balance every time we operate an aircraft. A couple of things that we can control would certainly be our payload, which discussed in our terms is the crew, the persons that we carry as passengers, and any kind of cargo will be our payload. So we can control that. The other thing that we can control is our usable fuel that we put inside the aircraft. So those are a couple of methods that we can use when we make calculations. I guess a couple other key things to keep in mind would be when it comes to any kind of addition of weight to the aircraft. Anytime we make an addition in the weight of this operating equipment, standard operating equipment of the aircraft, any optional equipment, that has to be listed inside the weight of balance and inside the maintenance records of the aircraft. However, there's such thing as a negligible weight change. And a negligible weight change would be an aircraft under 5,000 pounds. If we change that weight, the operating equipment, by 1 pound or less, we're not required to make any kind of changes to the weight and balance. For aircraft between 5,000 and 50,000 pounds, Um, we have anything 2 pounds or less is considered a negligible weight change, and then for very large aircraft over 50,000 pounds, we have 5 pounds or less as far as whether we have to take a look and update our weight and balance. There's also any kind of significant change in the CG, a negligible change in the CG where we wouldn't have to take a look at weight and balance would be anything less than 0.05% of the mean aerodynamic chord. Okay, we'll talk about the methods that we use to calculate the total weight of the aircraft and also the aircraft's center of gravity. And the first one is called the computational method, and this is the type of method that we use with our Duchess. And the things that we need to know would be the max gross weight of the aircraft and the forward and aft CG limits, which are expressed here. Forward CG limit for the Duchess is 110.6 and the aft is 117.5. Now, the next thing that we need to know is the things that are part of our control, the things that we're able to load in the aircraft. That would be, for example, the front seat, the rear seat, the baggage area, and the fuel of the aircraft. But what we're going to do is we're going to total up all the weights for those items that we've added. And then we also need to know the basic empty weight of the aircraft, which, of course, we can't control, but it's part of the computation. So we would take all these weights and we would have the total weights listed down there. Now, inside of the POH, for each of these stations, front seat, back seat, baggage, and fuel, we're given an arm. And that arm is to be multiplied by that weight to produce a moment. So we make that calculation. Weight times arm equals moment for each station that we've loaded inside the aircraft. And there's also one that's given to us. It's usually already calculated into a moment for the basic empty weight of the aircraft. So at that point, what we'll do is we'll add up the total moments of what we've loaded into the aircraft plus the moment that's given for us based on the standard or basic empty weight of the aircraft, which will produce total moments. So to calculate the CG at that point, what we're going to do is we're going to take total moments and we're going to divide that by total weight. That number will give us our center of gravity. The center of gravity has to fall within the forward and aft limits of what's provided for us in the POH for the forward and aft center of gravity limits. So if we fall within 110.6 or 117.5, our center of gravity is good enough to let us fly, provided that we are at the less than the max gross takeoff weight for the aircraft.
Okay, another method we have to compute weight and balance based on the aircraft's POH and the way it wants you to determine weight and balance is called the graph method. And if you look in the weight and balance information, the maintenance log of the aircraft, it will have the maximum or the basic empty weight of the aircraft, which is your standard empty weight plus optional equipment, avionics, and such. And then it will also have a moment associated with that. And then if you look at the POH, it has a graph. It will look something like this, where you can see it charts out weights and moments for passengers, fuel, baggage, and stuff like that. And we'll get to that in a moment. And you'll have a form you can fill out, a sheet. We've made one look like this, where you have the aircraft, and you have your basic empty weight, and the moment associated with that. And we just made a quick example here. We have pilot, front passenger, so we're assuming a solo operation. The pilot weighs 150 pounds. So we go to the graph that would be in our POH, and we find where it says pilot and front passenger. We follow our graph up to where it intersects with the 150 pound weight. We drop straight down from there, and we see a moment noted by the moment divided by 1,000. So this situation, we're 6.5. So 6.5 in that case would actually be 6,500. But we've divided these numbers by 1,000 just to make the numbers more manageable. So we go back to our sheet we're going to fill out to compute our weight and balance. And we have 6.5 for our moment for our pilot. Now our fuel at 40 gallons, we have to make sure that we take the gallons times 6 pounds per gallon for avgas. Make sure you don't compute the weight and balance based on gallons. You have to convert that to pounds. So that's a common mistake some student pilots make. So we figure out 240 pounds of fuel. We look, there's another line for our fuel. That's 6 pounds per gallon. So go ahead and it says that for you. That way it alleviates some confusion. So we follow this up to 240 pounds. And even has a note for 40 gallons right there. Drop that down. And we're at 12.5. So it'd actually be 12.5 thousand. Since all the moments are divided by 1,000, we write 12.5 on our sheet. In a solo operation, we don't have a rear passenger, so we'll put 0 on that. And we're saying for this example, we're carrying 50 pounds of baggage. So again, we go back to our graph. We find the baggage compartment area. And 50 pounds of baggage is going to get us a moment of about 7,000. So what we have to do is add up all the weights of the aircraft, the basic empty weight, plus the fuel, pilot, passengers, baggage, anything we're carrying on there that's not computed in the basic empty weight, and add that number up. And we take our moment, which we must include the moment of the actual aircraft itself, its basic empty weight, plus all the fuel, cargo, all our payload in essence. Then we have a total moment. We take the total moment divided by the total weight of the aircraft. Total weight of the aircraft divided by the total moments to give us our CG. So we have our total weight of our aircraft and all of the payload we're adding, and our total moments of the aircraft. And then we have a chart, also found in the POH, that shows our CG envelope. And what this basically is based on the weight and the moments we have to cross-reference. So in our situation, our aircraft weighs 1,924 pounds. So 1,924 pounds. And our CG, 84.7. And we're right here. So yes, we are within the weight and balance for the aircraft. And these were just made up numbers anyway. And this is not necessarily a weight and balance for the aircraft we're using. This is just for demonstration. But it shows that we are within the normal category. You can see we have a normal category and a utility category. As we mentioned earlier, the difference in those is the ability of the aircraft to withstand a certain amount of loads, and you'll find more information on this in your POH or AFM.
Okay, sometimes after we've made our weight and balance calculations, some situations arise. Things could be anything from we have to take some fuel out of the airplane because we're over max gross weight. We need to shift some baggage around in the aircraft. We've got some weight changes, such and so forth, and we can either go ahead and recalculate a brand new weight and balance. We can try and problem solve that way. Fortunately, all of this stuff is proportional and gives us the opportunity to use a couple of standardized formulas. We have a formula that we use for weight shifting, and we also have a formula that we use for any kind of weight addition or removal, and those formulas are very similar, so we'll go into a little bit of detail on those and give a couple examples. First of all, the formula itself for a weight shift is we're going to take the weight shifted divided by the total weight of the aircraft. Okay? And that is going to be equal to the change in the center of gravity. Because if we shift weight in the aircraft without taking or removing anything, we're going to have a change in the total moments. And that's going to move the center of gravity forward or aft. So it's going to be the delta, which is the change in the center of gravity. And we're going to divide that by the distance that the weight shifted. The formula looks like this. Okay? So the book, Chapter 9 of the PHAC, gives us a couple examples, and we'll use those to show you how easy that the formula is to use. Okay? Requires a little bit of common sense, but so we'll cover that. Let's give an example of we need to shift 100 pounds in the aircraft from, say, the front baggage compartment to the rear baggage compartment. Well, we're going to need to know a few things. Let's start filling in our blanks here. Well, we want to shift 100 pounds. Okay? And let's say the total weight of our aircraft, per the example, is 8,000 pounds. Well, I need to know what my new center of gravity is so I can determine if I'm within the forward or aft CG limits. Well, let's talk about the distance shifted. I moved this 100 pounds from the front baggage compartment at station 30 to station 150 in the back. So to determine that change, I'll subtract 30 from 150, and I notice that I made a change of 120 inches here. So then I can just fill that in to the formula over here. Okay? So 120 is my change in inches. So then I just have to do some simple math. And that's where a lot of people might get hung up on this. The way to do the math is just to do the side that you can, which is 100 divided by 8,000. And then I just simply get that answer, which is 0.0125. I'll simply multiply that times the information that I have on the other side. So that gives me a change in the center of gravity of 1.5 inches. So if I had a center of gravity of, say, 80, I can add that 1.5 inches because I'm moving from forward to aft. 1.5 inches. I get a center of gravity of 81.5. Conversely, if I took baggage from aft and I moved it forward, I would subtract that 1.5 inches. So that's one way that we can use the formula for a weight shift. Now, let's say our aircraft has a center of gravity after we did our calculations, and that center of gravity happens to be aft of our aft CG limit. So we need to move the center of gravity forward of the aircraft. And we're not going to remove any weight from the aircraft. We're just going to move some stuff around in our baggage compartments and try and create some different moments. So the way that we figure that out is we're going to use the formula in the same way. We're going to take the information that we have, okay, the total weight of the aircraft, which in this example in the book it's just a little bit different. It uses 7,800 pounds, okay, and we have to take a look at how far we want to shift our center of gravity. We want to shift our center of gravity in this example. We've got the center of gravity at 81.5 inches. And to be within our aft center of gravity, we need to be at 80.5 inches. Okay? So we need to take a look there. That's a difference of 1 inch. So we need a 1 inch movement in our center of gravity. So that change of center of gravity goes up here. We need a 1 inch change. Okay? From that point, let's talk about the distance that we're shifting the weight. Earlier we discussed we had station 150 and station 30 were our baggage areas. So we're going to be making a movement of 120 inches. So the distance that the weight is shifted goes in over on this side. So that's 120 right over there. So we're trying to make a calculation up here of how much weight that we need to shift per the formula. So let's figure out the side that we can figure out. So 1 divided by 120 is equal to 0.0083, and then we multiply that by the given information that we have on the other side, so times 7,800 equals 65. So we need to move 65 pounds from the aft station to the forward station to move that center of gravity 1 inch forward. Pretty simple. So now let's talk about how we can use this formula for a weight shift. And there's a simple modification that we do to the formula, and that's the added weight rather than the weight to be shifted divided by the new total weight okay, and then that is equal to the change in the center of gravity divided by the distance between the weight and the old center of gravity. So that's what it looks like right there. Okay? So let's take a look at an example that we can use this for right now. So we want to determine the change in the center of gravity if we add 140 pounds to station 150 in the back of the aircraft. Okay? So the way that we do this is we'll take a look at what information do we have. Okay? We're given the aircraft total weight here of 6,860 pounds. And what we're doing is we're adding 140 pounds. So let's fill in the information that we have. We're adding 140 pounds. Okay, so our new total weight is going to be our prior weight, 6,860 plus 140. That is going to be equal to the change in center of gravity, and that's what we're trying to determine. What's the change in center of gravity when we add that 140 pounds to that aft station? Change in center of gravity. And then we're going to figure out the distance between the weight and the old center of gravity. So our old center of gravity, we'll call that 80 inches. Okay, and then we're going to be adding that weight to the 150 station. So 150. All right, now we'll go ahead and figure this thing out. So first thing we'll do is we'll simplify a little bit. 6,860 plus 140 equals 7,000. So that's our new weight once we've added the 140. And then we're going to go 150, which is where we're adding the station, and minus the old center of gravity gives us 70. So now let's just solve the rest of the equation. 140 divided by 7,000 equals 0.02. And then we multiply that by the information we have on the other side, times 70, is equal to 1.4. Okay? So our center of gravity at that point, since we added weight to the aft of the aircraft, is actually going to move aft. So our center of gravity was 80 plus 1.4. So now we have a new center of gravity of 81.4. Now, what's the other way that we can use this formula? Let's talk about removing weight from the aircraft. So let's say we've determined that we'd like to remove 100 pounds from station 150. Okay? So instead of added weight, we use subtracted weight here. It's a total of 100 pounds. And let's say our aircraft is a little bit overweight, it's 8,100 pounds, and we're going to subtract that 100 pounds. Okay? That is equal to, what's our new center of gravity going to be? Change in center of gravity, and that's going to be divided by the distance the weight was moved, and we're moving that from station 150. And our center of gravity was 80, so let's solve this. That's going to be 70, and that's going to be 8,000. So if we go 100 divided by 8,000 equals 0.0125. Multiply that by the given information on the other side, 70.875. Nope, I did that incorrectly. I was actually going to use 6,100 pounds here instead of 8,000. Minus 100. There we go. So let me just start the formula over. I've got 6,000 pounds over here. So 100 divided by 6,000 is equal to 0.01666667 times the information I have given on the other side, which is 70. And what I get is 1.2. So from that point, when I remove that weight from that back baggage compartment, my center of gravity is going to move forward 1.2 inches because I'm taking weight off the back. So if I had a center of gravity of 80, I'm going to subtract that 1.2, and that's going to give me 78.8 inches. Conversely, if I remove that from the front, which is before the center of gravity, I would add that 1.2 inches. So that's pretty much how we use that formula.